Testing, testing. Okay. All right, hey guys, my name's Ishan. I have a background in AI and now I work as a software engineer at Microsoft. So I'm going to be talking to you guys about running inference, fine-tuning, and RAG on Kubernetes. So we've built something called Kaito, and that allows you to really efficiently run AI workloads on Kubernetes the easiest way possible. So I'm going to show you how that works. So we'll start out with some background, then we'll get into Kaito, the design of Kaito, the future roadmap, and then I'll leave time for Q&A. So just to give you some background, yeah, neural networks are not new. AI is not new. Like since the 1990s, we had simple n-gram models, and n-gram models are just ways that they could look at the past n words and then probabilistically determine the next word in the sequence. So when you type on your phone, it can give you a recommendation on the next word. Those are just simple n-gram models. Then we transitioned to the 2000s. We had neural networks. So those allow you to, the big thing that we were able to do was take words and represent them numerically as vectors. And that's that's word embeddings. That's still a huge cornerstone of LLMs today. And then, of course, we start to get more powerful models, so they're more context aware. And then finally, we have LLMs, which are powered by the attention mechanism. So they're powered by the transformer architecture, which was released in 2017. And I mean, not only are they super context aware, but they're also really accurate. And they're really able to understand the context of what you're trying to say, even without you needing to say it. So it's super impressive. But obviously, there's limitations, right? So these models are huge. GPT-4 has 1 trillion parameters in it. Various open source models will be in the billions of parameters. And as the model sizes get bigger, the number of tokens you need to train actually goes up exponentially. So it's super expensive to do inference, to do training. And I mean, for example, GPT-5 is rumored to have 10 times the amount of parameters. So it's like, with 10 times the amount of parameters, it's going to cost 10 times as much per inference call, roughly, right? So, this, in essence, in a practical sense, this is an infrastructure problem. And we need to solve this from an infrastructure perspective. And this is why we believe Kubernetes is the best solution. So why would you want to run LLMs directly on Kubernetes, right? That's the next question. Obviously, I want to address there are hosted solutions. Like there is Azure ML, there's AWS SageMaker. There are solutions that abstract away Kubernetes, and they provide you an endpoint or something that you use. So with regards to Kaito, with what we're presenting, why would you directly want to run LLMs on Kubernetes? Well, you can bring your own data. You can bring your own data, you have your own infrastructure. So in terms of data and security compliance, you get to control the sensitivity there with that. As you can also control the localization of your data, where your data is located, what permissions you have on it. You obviously also have the observability over your own infrastructure. So you get to actually see what you're doing. You get to set quotas for your infrastructure, and then you have the customizability. You could all the networking settings, configurations. You're getting to bring your own infrastructure, and the community is completely ready for you to do this. I mean, Hugging Face has all the models, the benchmarks, the data sets, and there's a whole bunch of ML engines out there. There's VLLM, Onyx, DeepSpeed. So the case for using Kubernetes is clear, but it's not easy. Right? I mean, Kubernetes is hard, and AI is hard as well. So you need to be able to, obviously, when you're running AI workloads, you need to maintain large model weights. I mean, billions of parameters. You need to be able to host these models somewhere. You need to have the GPU infrastructure for the models. You need to, parameters. You need to tune the parameters for inference, for fine-tuning, for RAG. And then, of course, you need to be able to know about the specific NVIDIA drivers and configuration and libraries. And then you have to set up a server in the end. So this is where Kaito comes in. I mean, we want to take all those trivial things, those unsexy things that you have to do, and make sure that you don't have to worry about it, right? So Kaito stands for Kubernetes AI toolchain operator. So we obviously use Kubernetes. As I was describing earlier, we're not a like Azure ML or SageMaker. We're a we're not a platform. We're a CRD. We take the CRD approach. We're literally we're a controller, right? And then obviously we streamline your workflow, so we take care of all that stuff that I was describing earlier on that slide. You wouldn't want to have to do yourself. And this is really what's so cool. This is the example. This is our CRD, the workspace CRD. This is the magic of it. It's super, super simple. I mean, all you need to do is specify the SKU that you want to use and the preset here, which is the model that you want to use. So, I mean, it can't get more simpler than that. I mean, we pre-provision the GPU for you, and we install the NVIDIA drivers and all the configuration that you need. And then we have images. So these are preset images that have the model weights in them. They have the workload and runtime configurations. We take care of running the service and the deployment. Depending on the model, we'll use a stateful set as well, like for sharding. So we take care of all the setup there with the model architecture, making sure that it can run correctly. And then, of course, if you do want more flexibility, we do have the option for you to use a preferred node. So you could use your own node, and you could also set a custom template. So you could include your own Python template if you do want your own Python server code, if you do want that flexibility there. How do we provision nodes? So we use Carpenter Core APIs, so that's vendor agnostic, to provision our GPUs. And that allows you to specify. So why would you do that as opposed to auto-scaling? Auto-scaling, you have pods stuck in pending, and then that triggers scaling up nodes as opposed to specifying them up front. This allows us to do some pre-flight validations. We actually check if the model can run on the hardware that you specify. We check if it has enough GPU memory. So we're literally taking care of that. And yeah, we also give you the flexibility to use whatever SKU you want because we're pre-provisioning it. One thing is that we do store the model weights in the images themselves, and this is something that was done intentionally. In terms of, so the model weights are never changed. We're only reading the model weights, whether it's for inference or RAG or fine tuning, and so we don't. For simplified version control, we store the model weights in the image itself, as opposed to putting it in blob storage or something like that. Because if we did that, we'd have to create some version control mechanism to be able to then update our images. And we also do this for ease of distribution. By keeping the weights in the images themselves, we can allow MCR to replicate the data in different regions and be able to distribute the images easier. It's more cloud native friendly that way. So yeah, that's what we do there. And so then this is the example here. This is we host the images, right? So we host them on MCR. The images, but those are images that are only Apache 2 or MIT licensed model weights. So those are public. So yeah, it's all hosted for you. So that includes Falcon. We have Falcon, Mistral, all the Phi models, and perhaps a couple others that you can see. I'll share a link later. Okay, sadly, not all models are Apache 2.0 or MIT. So Llama, for example, is a private model. And if you do want to build your own image with your own model, you can. We give you a Docker file to do that. And you can simply build your own image, but you'd push it to your own container registry. And then we would just pull it from there. So ACR or whatever container registry you want to use. I'm not going to spend too much time, but this is just a diagram of how everything works. So the big thing to take away is step 1 there, which is you creating your CRD that I was showing earlier. That creates the workspace CR, which goes ahead and creates the machine CR, which creates the actual GPU for you. And that GPU node will then pull down, if it's a public model, it'll pull it down from MCR, otherwise it'll pull it from your private registry. And there you go. Then you can run your AI workload. But the real big thing here is that it's like the easiest way, especially that I know of, like the easiest way for you to get started running an AI workload on Kubernetes is you just install our Helm chart and you just, because we're hosting the model weights and everything for you already. So it's the easiest way to get started. And we also support RAG and fine tuning now. So it's not just inference. You can run RAG workloads, fine tuning workloads. Are you guys familiar with RAG? I think, okay. I can give like a very quick primer. This is an example I've used before, but but like one of the examples I like to use is like if you ask ChatGPT, what is my favorite meal? GPT has no idea what your favorite meal is, obviously, right? So if you also had a vector DB with all your DoorDash history in it, now you could provide like context for GPT. So now what happens is you prepend to the prompt, what is my favorite meal? The DoorDash history that you have. And now GPT knows, like it can answer what that is. So that's essentially what RAG is in a nutshell. It allows you to prepend context to the prompt that the model otherwise wouldn't know, right? So that's what RAG is, and it's super popular now. And the other method that people use for getting additional, the other method people use for trying to take base models and solve specific problems is fine tuning. So we support LoRA and QLoRA as well. So what that does is you take a base model which already has generalized knowledge, and then you add adapters. They're called adapters to it. Adapters are just they represent 1% to 2% of the original base model's model weights, and you literally add them on, and it allows you to specialize for a specific task. So if you can have LoRA adapters for coding is a popular one. So now your LLM is specialized for coding once you add those adapters into your model. And we can talk more about that later. But I hope that gives like enough context there. So this is what I really want to talk about here. So this is what it ends up looking like. This is what our fine-tuning CRD looks like, and this is what ends up happening. Again, super simple, right? So just like we had presets before, you specify a preset, you specify the method, either LoRA or QLoRA, and then you specify your input data source. So this is where we download the data from. So it's just like either a set of URLs or it's an image. And then we have the output image here. So we'll just push to whatever container registry. And this output would be the adapter. So what I was talking about earlier. And that adapter then gets added onto the model. So now you might also be wondering, where do you put like the fine-tuning parameters like epoch and learning rate and stuff like that? That goes in the config template. We already have a default config template for each model that we provide with like just basic settings. But if you want to customize it, you can, and you just make a config map and you just apply it. So yeah, you can get up and running with fine-tuning like literally like that. And then what ends up happening is we create a job. We download the data first, your fine-tuning data. We run the model, and then when the result is outputted, we have the sidecar container that pushes your output to ACR. So, and we can come back to this and answer any questions. And then this is the next piece here. So once you've done that, now you have these adapters. You want to add them onto your model. This is all you have to do. You specify the adapters you want to add. And we have a field called strength. By default, it's 1. You don't have to add this. But nowadays, people are adding multiple adapters and playing around with that. So we have the ability to do that. And you could specify strengths for each of them. It's commonly used in stable diffusion a lot. but also in LLMs, people will use that. Okay, and we can come back to those slides if there's any questions. Okay, this is the last part. I was going to talk about RAG. So we do support RAG. There's a couple different components of RAG. There's obviously the storage. So we have a vector DB. By default, we use FICE in memory. But we also support ChromaDB, and we're supporting Cosmos DB as well now. And so that's remote storage there. As far as the embedding model can either run locally on the hardware that you specify, or we can have it run remotely, either via URL, or these days actually Hugging Face even can give you an endpoint that you can use to run an embedding model. Embedding models are a lot easier because they're only in the hundreds of millions of parameters, not in the billions of parameters. So you can even run some of them on CPU as well. Then we have the inference. So inference is just going to be a URL. The vision here is that it could literally be a Kaito workspace, is just the URL. So you have a workspace, CR that you've created, and then you have the RAG engine CR, and they can interact with each other. So they're like building blocks. So as far as compute resources, you specify where your RAG server is going to run, and if you do specify a local embedding model, that'll also run there. And then we're using, I just thought I'd include this, we're using Llama Index. You can also use LangChain, but that's the orchestration library that we use for setting all this up. Yeah, so super simple. You specify the DB that you want, you specify the embedding model, so in this case it's a Hugging Face model ID, and then you specify the inference service. So in this case it's just a cluster IP of a workspace CR. And then we spin up the RAG server hits the embedding model, which is running in it, and the vector DB. So in this case, it's FICE DB, which is an in-memory vector DB. But we also support Cosmos, so Cosmos would run outside of this. This is how it should be. This is how simple it should be to do basic fine-tuning, basic RAG, basic inference. It should not have to be more complicated than this, and it is right now. So that's why this is so important, and that's why you guys should try this out. We are collaborating with upstream working groups, working group device management and working group serving. We provide our use cases, what we're working on. They give us feedback. This is the last slide I have here, then we'll do Q&A. So we released almost exactly a year ago, and we support dozens of models currently. I believe we support like 10 or 12, and we want to support dozens more. The next release will have the RAG engine in it, and we're also an onboarding to CNCF sandbox project. So we're also seeking new collaborators, maintainers. This is an awesome opportunity for anyone interested in AI infrastructure, Kubernetes and AI. And it's not crazy complicated either. It would be a good project if somebody just wants to get involved as well, or if somebody wants to do more advanced stuff, there's also opportunities there. So it'd be an awesome opportunity. That's our GitHub, and I will do questions now.
Okay, so my first question is, I have multiple. Is Kaito specific to cloud providers? Can I just bring my own infra and then let Kaito do?
Yeah, it's vendor agnostic, so you can use any cloud provider. We're using Carpenter Core APIs, so you can use AWS or Azure, and if you want to use GCP, you could specify a preferred node. So you can use any cloud provider. I believe so as well. Yeah. The question was, can you use any cloud provider? Is it cloud agnostic? The answer is yes, it is. So we use Carpenter Core APIs, so we can use AWS or Azure. For GCP, you'd have to specify a preferred node. So you would have to provision the node yourself, but once you do that, you just specify it in the spec, and we would take care of using it. Yeah.
How's it going? Thanks a million. AI novice here, but what I do know is that the preferred kind of toolkit for running AI workloads in Kubernetes at the moment is Kubeflow. I was just wondering, first of all, how does this kind of compare to Kubeflow? Would this be kind of like an equivalent kind of offering, or does it kind of fit better as a component of Kubeflow? Because I understand that Kubeflow is just a set of components.
Yeah.
Secondly, one of the things that you said a good few times is that this is very, very simple. And one thing that I do know about Kubeflow is that it's very, very hard to at least get set up in Kubernetes. So how does it fit in?
Yeah. So I'm not an expert on Kube, but I know there's Kubeflow, and I know people use, I think Ray as well, right? Kubeflow, I have tried getting set up with Kubeflow. I did run into issues. They have their own, I think parts of the project are archived, but they have their training operator. So I know people use it for training a lot. I don't know if it supports inference, and I don't know how they're taking care of. We obviously put the model weights in the image itself. I think you would have to build your own images, I'm guessing, to then use Kubeflow, and then you'd have to make sure that they're compatible and you build it in the right way. So I do think it's from what I remember using it, it's fairly complex to get set up, and I wish I knew more about that, but yeah, that's.
So you're using Carpenter to do auto provisioning, but how are you doing auto scaling across so many different frameworks that when you want to do fine tuning, you want to do RAG, I don't know how you would take a look at the load and determine that you need more nodes in your node pool.
Yeah, that's a great question. We currently don't support auto scaling for that reason. We are still working on that. We do have metrics that we've started to gather with GPU usage, and based on that, we will determine auto scaling, horizontal pod auto scaling, and then from there, we're also working. Some members of our team attend a lot of the DRA meetings because that solves a lot of the issues there with auto scaling as well as MIG. So we still haven't. That's still a complex issue, and that's obviously the next step is being able to auto. I think everybody's working on that right now. The whole Kubernetes community is. So yeah.
More questions?
Can I just, while deploying or using a model, can I just specify any Hugging Face ID and then you pull the model, or it has to be a container image to be able to use that model?
So yeah, like a Hugging Face model ID? Yeah, so if it's not one of the presets that we support, you can build your own image using a Hugging Face model ID. So we provide the steps for how you would do that. So if it's not one of our supported models, you can just download the model from Hugging Face and use it. You can just in our Docker file, and it'll build it for you.
And a lot of models, depending on how they're trained, they also have different backends, right? So how do you differentiate between what backend is supported and what's not? There is CPP, Llama CPP, and then there is.
Okay, yeah.
There are a bunch of them. I don't have a lot of experience, but from what.
Yeah, there's different quantized models. There's GGUF, GGML. Right now we use. I actually should have mentioned this. We use VLLM to run our models. So it does need to support the VLLM engine. However, we also have there's a setting. If you don't want to use VLLM, you can use Hugging Face Accelerate library as well as the runtime engine. So those are the two runtime engines we support: VLLM and Hugging Face Accelerate. If you don't use one of those two, so for example, if you're trying to run Llama CPP, we unfortunately don't support that. Right now, but you can use Llama, the non-quantized version, and we do want to support more engines, Onyx, DeepSpeed, and serving frameworks as well. But yeah, that's all we support right now. You have a question?
Can you tell me a little bit more about pre-provisioning the nodes? What do you mean by pre-provisioning the nodes over there?
Yeah, pre-provisioning means that we I feel like it's more complex than it needs to be. We just make the node for you in advance, as opposed to auto-scaling, which is you create the pod and there's no node, and it's stuck in pending, and that triggers creating a node. Does that make sense?
So like when I'm deploying my inferencing, you will provision a node and
Yeah, we already know that you need a node, and we'll
because
make
I'm
it for
deploying
you.
inferencing, right? I'm deploying the inferencing, that's why you know it.
You're specifying it up front that this resource I want created, I want my code to run on this.
Okay.
Yeah.
Yeah.
We can chat
so,
after.
Yeah, sure.
is
Yeah.
that-
Just to add that Kserve is the serving side of Kubeflow, and it also does VLLM and Hugging Face Accelerator. So I think this is the same
Right,
model.
right.
Yeah. So right now, with respect to allocating a GPU, do you like allocate the entire GPU? How do you know, like, or can users specify? Can they even specify like a less than one kind of like one GPU using MIG or whatever?
We were trying. We're working on MIG right now, but right now we use the whole. It's like one pod per node, so we use the whole GPU. With DRA, we hope that will become a lot better because you'll have MIG instances. You can schedule different things. Things can get shuffled around, and that'll make for a much more powerful, heterogeneous environment. Yeah.
What is the recommended node size for run these models?
Yeah, so that's a good question. We have some benchmarks that we did about that. So some of the 7 billion model parameters, Falcon 7B, Mistral 7B, you can run in a 16 GB V100. However, once you get to, it grows linearly. Once you have larger context length, you're going to use more GPU memory. So if you test the upper bound, you can get an OOM. So now what we have, we actually included this in our VLLM code. We test what's the max model length that you can use with that GPU that you provisioned, and we cap it at that. So we make sure that you don't OOM because we make sure that, yeah, you don't go out of memory there. So that's a really good question. That's something that we take care of. Yeah.
More questions? All right. Going once, going twice. Thank you very much.